Welcome to this module on iteratively reweighted least squares. The name is rather intriguing and builds some suggestions for what this module could possibly be about. Least squares, of course, is a technique which you are all familiar with. You have visited this in the preliminary regression classes and seen that it can often lead to techniques with very good estimators. In many situations where least squares is not directly applicable, we can often transform the data so as to make a variant of least squares applicable. You have thus heard of generalized least squares. In this module, we are going to talk about iteratively reweighted least squares. The name suggests that there is some iteration, and reweighting suggests that there is some reweighting which needs to be built into the least squares at every iteration. The technique is something which we use for solving the score equations for the generalized linear model, and in this module I'm going to go into the exact steps and simplifications in case we have a canonical link. The learning objectives for this module: first, we will revisit the derivation of the score equations for the GLM. We derived this in the earlier module. Next, we shall look at means of solving these score equations using two algorithms, the Newton-Raphson and a variant called Fisher scoring. We shall define something called iteratively reweighted least squares. This is the algorithm which is used for actually solving the equations. And finally, we shall see that there are some simplifications in the case where we have a canonical link. Now, to quickly recap, the one-parameter exponential family in its canonical form is given by this form of the likelihood. F of y theta is equal to exponential of y theta minus b of theta divided by a of phi plus c, y and phi. Theta is not necessarily the natural parameter, but is something called a canonical parameter, which is a one-to-one transform of the parameters which we normally use to index the one-parameter exponential family. Phi is an optional scale parameter which may or may not be present. The second component of the one-parameter exponential family is the linear predictor eta, which we define as eta equal to x prime beta. X here is a p-vector of known covariates, and beta is my unknown vector of regression coefficients. I then relate the random component of y to the fixed component eta using a link function g, and the equation g of mu is equal to eta. Maximum likelihood estimation for this family. Note that assuming a single observation, we can write the log likelihood as L of theta y equal to y theta minus b theta by a phi, so that using the chain rule, del L del beta j can be written as del L del theta into del theta del mu into d mu d eta into del eta del beta j. The components of this are given by del L del theta equal to y minus b dash theta over a phi equal to y minus mu over a phi, using the fact that for one parameter exponential families, mu is equal to b dash theta. Del theta del mu is equal to 1 over b double dash theta equal to 1 over v mu being the variance function, or alternatively this is equal to a phi over variance of y. We have used the result that for one parameter exponential families, v mu, the variance function, is given by b double dash theta up to a scalar a of phi. Del eta del beta j is of course xij, the value of the corresponding covariate. Putting all this together, the form of the score function is given by del L del beta j equal to y minus mu over variance of y, del mu del eta into xij. For canonical link, we have some simplifications. For canonical links, we have said that eta is equal to theta. So for the normal family, for example, this means that eta is equal to mu, leading to usual linear regression. For the binomial family, eta is equal to logit of pi, which gives me logistic regression. For canonical links, there is also some simplification to the score function. So del mu del eta is equal to del mu del theta, which is equal to b double dash theta. Substituting this into the score equation, we get del L del beta j equal to y minus mu over variance of y, b double dash theta xij. And using the fact that variance of y is b double dash theta, we get the simplified form del L del beta j is equal to y minus mu over a phi into xij. The information matrix is similarly given by minus of expectation del square L del beta j del beta k, which by properties of the one parameter exponential family can be written as expectation of del L del beta j into del L del beta k. Using the calculations which we have derived so far, this is equal to expectation of y minus mu over variance of y whole square into d mu d eta whole square into xij xik. Using the fact that expectation of y minus mu whole square is the variance of y, this simplifies into 1 over variance of y d mu d eta whole square into xij xik. The score equation then for one observation is given by del L del beta j equal to y minus mu over variance y d mu d eta into xij. Combining all the n observations from the data set and all the p components of beta, for n observations, the score equation is given by del L del beta equal to x prime a into y minus mu equal to 0. I leave it as an exercise to you to find out the explicit form of matrix A. The information matrix similarly can be simplified. So minus of expectation del square L del beta j del beta k is equal to 1 over variance of y d mu d eta whole square into xij xik. If I combine the observations for the entire data set and I stack the equations for all the p parameters, it turns out that in matrix form, minus expectation del square L del beta prime is equal to x prime wx. Again, I leave it as an exercise for you to find out the explicit form of the weight matrix W. Let us come now to the solution of the score equations. Just taking a look at the equations, you can see that they can be written as the sum of n terms from the n observations in the data set, where each term involves my parameter of interest beta in a rather complicated way. So the meaning of this is that it is not really possible to separate out beta from the rest of the terms, and hence the solutions cannot be written explicitly. For linear models, by contrast, we know that the score equations turn out to be of the form x prime y minus x beta hat equal to 0. And since there is a single well-behaved term using the regression coefficient beta, it can be transposed to get an explicit equation for beta hat as beta hat equal to x prime x inverse x prime y. For the generalized linear model, such manipulations are not possible, and thus we just end up with an equation say S of beta hat equal to 0, where S is the score function, and the definition of my maximum likelihood estimator of beta hat is thus that value of beta which is the solution to this equations. That is, there is no explicit equation which I can give you for the form of beta. Now you all know that when we have an equation of this form, the approach to this is to use numerical methods. You may be familiar with numerical methods. There are a large variety of numerical methods. Some of these use information on the gradient and some of these don't. For example, you might have heard of something called the bisection rule, which does not use gradient information. And you may have also heard of something called Newton-Raphson, which uses information on the first and second derivatives. Now, gradient information also can be supplied to an optimizer in several ways. For example, you could ask it to compute the numerical gradient at each step, or you could supply the value of the analytical gradient. Now, the score equations for the generalized linear model, though complicated, are sufficiently well behaved analytically that it is possible to compute the first and second derivatives analytically, and thus we shall use the Newton-Raphson algorithm for solving the score equations using information that is analytical information on the first and second derivatives. Actually, it turns out we will use a variant of the Newton-Raphson. This variant is called Fisher scoring, and it is a variant in the sense that it does not use the observed information but rather the expected information. Finally, we shall see that implementation of Fisher scoring leads to an algorithm which is called the iteratively reweighted least squares. And you can see that this is a highly suggestive name and suggests that even though the least squares is not directly applicable here, it turns out that at each iteration we do have to use a certain form of least squares to get the maximum likelihood estimators for GLNs. Fisher scoring algorithm. If I write out the steps of the Newton-Raphson algorithm, which say that given my iteration at t and the results from the tth iteration, say beta t plus 1 is equal to beta t plus a correction factor which depends on the Hessian or the information and the score at iteration t. If I take one simple step of replacing my observed information by taking an expectation over it, I get the equation which is written on this slide. This says that beta t plus 1 is beta t plus a correction factor which can be expressed as x prime wx whole inverse into x prime a into y minus mu. The iteratively reweighted least squares works in this way. Now note that beta t plus 1 equal to beta t plus x prime wx whole inverse into x prime a y minus mu can be rewritten in this form. Beta of t plus 1 is equal to x prime wx whole inverse into x prime wx beta t plus x prime a into y minus mu. How does this help us? Well, note that x beta is actually eta, and if you have found out the matrices A and W, you will see that they are related by the form A is equal to W into d eta d mu. This means that beta t plus 1 can be expressed more compactly as x prime wx whole inverse into x prime w z. Z is a variable which is called eta plus d eta d mu into y minus mu, where of course the multiplication means that it happens component wise. So what does this mean? If you note the form of the score equation, it is as if at each iteration a weighted least squares is being fitted not on the original outcome y, but on something called z, which is my working variate or adjusted dependent variate. The weight matrix is W and involves the parameter beta, and so it must be reweighted at each iteration. This could perhaps be made a little simpler if we consider a concrete example. So let us assume again that we are looking at a proportion, so that n of yi follows binomial ni into mu I. V mu I is then given by mu I into 1 minus mu I, and we shall assume the logistic model log of mu I over 1 minus mu I is equal to xi prime beta. Note that d eta d mu I is given by 1 over mu I into 1 minus mu I. The W matrix is thus W equal to diagonal ni mu I into 1 minus mu I. W is in fact the matrix of the variances. My constructed variable zi turns out to be equal to zi eta I plus y minus mu I over mu I into 1 minus mu I. Written as a function of xi, this is xi prime beta plus yi minus exponential it xi prime beta exponential it xi prime beta 1 minus exponential it xi prime beta, where exponential it refers to the function e to the power w by 1 plus w. So in the context of binomial regression, fitting an IRLS would involve first finding some initial estimator. We can do this by using least squares, using it to construct the variable z1, as also the weight matrix w. We can then fit a weighted regression of z1 on x using the weight matrix w, or rather say w1, to get the new estimator beta 2. We then update eta and hence also update z to get z2, that is a new form of my constructed variable. We also update the weight matrix w and again fit a weighted least squares. So thus we see a justification for the name, iteratively reweighted least squares. That is, we have a sequence of iterations. At each iteration we are fitting a least squares, not on the original variable but on z, and we are in fact fitting a weighted least squares where the weight matrix needs to be updated at each iteration. In this module, we have visited in detail the technique called iteratively reweighted least squares. You had all heard of least squares before, and this module emphasizes why it is such a fundamentally important building block in statistics. Now, we have written out the score equations for the generalized linear model and seen that they are indeed very complicated with no explicit solution. However, when we try to do a new variant of the Newton-Raphson algorithm, we see that it is possible to reduce it into an iterative method where every step involves fitting a least squares. not on the originally observed data, but on something called a working variate.